It's just about IBM SPSS and a few descriptive analysis. No? So today we will be focusing on analyzing data. Yeah, we will be reviewing parts of those we have discussed yesterday, and then with some focus on analyzing data using inferential statistics. So let me share my screen. So I would like to inform everyone that I will be skipping some of the slides, because obviously some of this we have taken up yesterday. And then I am sending two PPT files, which I'm going to discuss, to augment, what is being presented in this particular PowerPoint presentation. I would like to give you a thorough discussion of correlation and regression, because actually I have a very good material for this. So I will not be focusing only to this PowerPoint presentation. That's why I will be asking Nora to share the material, when we are already in the said topics. So again, please, if you have any concern or if you have any question, especially in what I'm going to present and what I'm going to discuss, please do not hesitate to ask questions. And then I believe that StrandAsia nor have prepared some prizes for some activities that we're going to have today.
Yes,
Nor?
sir. Yes, sir. No problem.
And the grand prize is the house and lot, no?
Ayun lang.
Okay, so just what do you call this?
Recording in progress.
Or perhaps just a model, no? So later we will be talking a model. Perhaps the grand prize nor is a model house and lot. Okay.
Picture, sir.
So let me proceed. So we will be talking about, so you notice that we have discussed already frequency distribution, the chart, no? So perhaps we will focusing more on starting here, no? Categorical versus categorical and so on. So perhaps this is just a review, no? So descriptive and inferential statistics. So the objective of this presentation to understand the different measures describing the distribution of the data, to learn the basics in testing hypotheses, so for descriptive statistics, you have the measures of central tendency. Now we are particular with the three most commonly used measures of central tendency. You have the mean, median, and mode. So you have the mean, that is the average. That is actually our concept of the average, no? And you have the median, that is the middle value that separates the higher values and the lower values equally. So that is actually the middle of a set of data. When the data are equally divided into two, no? So basically, if there is an odd number of data, and we have a median, the one at the middle, and then if there is an even number of data, we take the average of the two middle values. And then the mode is the most frequently occurring value, no? That is the value with the highest frequency. And if you have remembered yesterday, we have discussed the 4 levels of measurement. So, if the data are quantitative, it's either interval ratio, then the most representative measures of central tendency is the mean. While if the data is ordinal, ranking, so the most appropriate is the median. And then for the if the data is categorical, no, so the most representative is for the measures of central tendency is the mode. And then we also have the measures of dispersion. So the measures of dispersion from the word disperse, no? So dispersion, disperse meaning scatter, no? Or that is the spread, no? So we have the commonly used measures of dispersion. You have the standard deviation, the variance, and you know that the variance is just the square of the standard deviation. While the standard deviation is the square root, not the square, no? This is the square root, not the, yeah, correct. The square of the standard deviation is the variance, and here, the standard deviation is the square root of the variance. Basically, the two are similar, except that if you have your data, for example, in meters, no? So the standard deviation will give you the same unit for the data that you have collected, no? For the variance, it will be the square units of your data, whatever is your data. So it should be the square unit. But basically, the interpretation is the same. And then you have the concept of the minimum and the maximum. So the minimum and the minimum is the lowest value, and the maximum is the highest value. And then you have the range, is the difference between the highest and the highest and the smallest values in the data set, no? Although there are also other measures of dispersion, such as the quartile deviation, no? Quartile deviation, actually, that is the formula for that is the third quartile minus the first quartile divided by 2. So the difference between the 75th percentile and the 25th percentile, that is actually what you call the interquartile range. No? So if you divide it by 2, you get the quartile deviation. The quartile deviation, it's denoted by capital letter Q, and that is actually called also as the semi-interquartile range. The the interquartile range, Q3 and Q1, actually is very important, especially if you want to calculate whether an observation is an outlier or not. Okay, so that's why and then obviously if you use the mean as a measure of central tendency, then you have to disperse it with the use of either the standard deviation or variance. No, however, if you use the median as the measures of central tendency, then you have to disperse it with the use of the quartile deviation. Okay, so as again, measures of dispersion, from the word dispersion, dispersion is the degree to which numerical data tend to spread about an average value. So dispersion or spread or scatter, or sometimes this is also related to the measures of homogeneity or the measures of consistency and inconsistency. Now, because like for example, if the values of these measures of dispersion are lower or are smaller, it means that the data are closer. While if the values of these measures of dispersion are big or large, it means that the data are scattered, no, are spread out. Now, like for example, if the ages of all of you here attending this training, your all of you, your age is, let's say, 25 years old. All of you 25 years old. So it means that the spread of your ages is what? If all your ages, for example, all of you are 25 years old, then what is the spread of your ages? That would be 0, no? That would be 0. Okay, um just to point out my discussion about the use of the measures of central tendency and the measures of dispersion. Now, for example, you have okay, so you have can you see my screen, guys? Is my screen? Can
Yes, sir.
Okay. So this is three different sets of data, no? So, and then we talk about the mean and the standard deviation. So if you will check, no, the mean of set the first data set, the mean is 7 and the standard deviation is 0 because all measurements are equal. So therefore, the dispersion or the spread is 0. And then if you also try to calculate the mean of the second set, the mean is 7 and the standard deviation is 0.63. There is already a standard deviation because there are two values which are different from the others. And then the third scenario, or the third data set, the mean is also 7, but the standard deviation is 4.04, no? Because the values of this set is already dispersed, no? It's already more scattered compared to data sets B and A, or first and second. And then we talk about skewness. The measures of skewness. Skewness is actually the measures of symmetry of a set of data or of distribution. And then when you say symmetric, meaning not skewed, no? So symmetric or normal. And this means that the mean is equal to the median, which is equal to the mode. And then skewed to the right or positively skewed distribution. So meaning long tail to the right, no? So this one is skewed to the right, no? You look at the tail is going to the right. So it means that the skewness here is negative, and then you have, positive, and then you have a negatively skewed distribution. So meaning skewed to the left, no? So, or negatively skewed distribution, and the tail is going to the left, no? So you have there the relationship between the three measures of central tendency, no? If you talk about skewed distribution, either skewed to the right or skewed to the left distribution. I think everyone knows about symmetric or symmetrical distribution or normal distribution. And then you also have skewed to the right, wherein the mean is greater, no? If the mean is greater, that is skewed to the right distribution, while if the mode is greater, skewed to the left. Okay. Just like you, I do not know if you are familiar with this, no? How will you identify, no, based on the given values, no, without calculating the mean, median, and mode, no, whether it is skewed to the right or skewed to the left distribution? If there are many, for example, if you are given a set of data, if there are many small values or low values, meaning the distribution is skewed to the right. If you have a set of data or a set of observations wherein many are low, or small values, it means that this distribution is skewed to the right. But if you have a set of observations wherein most of the observations are high, it means that the distribution is skewed to the left or negatively skewed distribution. When I was still new in teaching, actually I have difficulty understanding these concepts about skewed to the right and skewed to the left. So I just got the technique, so I will have to draw it. I will draw, and then so the tail is going to the right, meaning skewed to the right distribution or positively skewed. And then I will draw the mean, the position of the mean, the mode, no? The mode actually is the one at peak, no? So this is the mode. The median is always at the middle, and then you have the mean. So the mean is here, meaning the value of the mean is to the right of the distribution. Isn't it, when we try to make or construct a graph, first we label, for example, here 0, and if the value is going to the right, meaning the value is increasing. No, so that is why you can easily observe. No, you of course this is your standard, the mode, and then you have the median at the middle, and you have the mean here. So it means that since the mean is to the right, it means that is the one that has the highest value. So if the mean is greater, that is skewed to the right distribution. While if you draw the curve negatively skewed, it means that the tail is going to the left, and of course this is the mode, again followed by the median and the mean here. So you notice that the mode is to the right. It means that the mode is greater. You understand? And then even if you do not draw it, no, if you do not draw the distribution, still you can determine whether the distribution by looking at the distribution, or the scores or the items. If there are many small values, meaning skewed to the right. If there are many large values, it means skewed to the left. No, and then I have observed that when I try to watch news, or I tried to read newspapers, the newscaster will just tell in her report that the distribution of the salaries of employees in the company is skewed. No, so he did not specify whether it is skewed to the left or skewed to the right. No, so we just try to make an analysis, so the distribution of the salaries in a company, for example, is skewed to the right. Okay, it means that when usually salaries, we talk about salaries, usually it's small, it's low, no? I have not seen perhaps siguro only a few, employees of the company not complaining about the salaries. No, so we would expect that when, for example, in the papers you read that the distribution of the salaries of a company is skewed, it automatically means that it is skewed to the right. It means that many are receiving low values, meaning the data you have many low values. Okay? And then when you talk about skewed to the left, for example, when you talk about sizes of shoes, what is the distribution of the sizes of shoes of basketball players? What is the distribution of the sizes of shoes of basketball players? So usually basketball players are tall, and tall people have big feet, no? And therefore they need bigger sizes of shoes. So it means that many will have bigger sizes of shoes. So it means that the distribution is skewed to the left. When you say, for example, what is the distribution of the scores of students in a difficult exam? If the test is difficult, you expect that many will get low scores. So many will get low scores. It means that you expect that the distribution of the scores of students in a difficult exam would be skewed to the right. When you talk about the ages of patients or people in the home for the aged, the ages of the residents of people or patients in a home for the aged, you expect that to be skewed to the left. I think that is very clear. Now, however, guys, when you talk about, for example, what is the distribution of the sizes of shoes of college students? Sizes of shoes of college students. You would expect that the distribution is symmetric or symmetrical or normal, no? Because the most college students have the average size of shoes. Now, that is why you notice in a department store, no, especially in their shoe department, they have many stocks of the average size of shoes. Now, they have only few stocks of smaller sizes of shoes and bigger sizes of shoes. So we would expect the distribution to be symmetrical or normal. If you talk about IQ scores, no, of college students, so usually when you talk about IQ scores no is considered to be normally distributed. The distribution of the IQ scores, no? I mean the distribution of the IQ scores of college students is normally distributed. But if you talk about exclusive schools such as, for example, if you talk about UP Diliman, you know, when you talk about, let's say, IQ scores, I do not know if you can consider that as negatively skewed. It means that in UP Diliman, there are those students who are below average. I don't know, perhaps, no? But basically, when you talk about, you consider all college students more have average IQ. Okay, so this is the guideline, no, to determine the skewness of the distribution. How will you know whether the data that you have collected is symmetrical or normal, whether it's skewed to the left or skewed to the right? No, there are some statistics, especially in the use of parametric statistical tools, no, that they require that the data should be normally distributed, no, for you to justify the use of such statistical tool. So two distributions have the same skewness value of 1. So you have two distributions and then they have the same skewness. The skewness is 1. And then the standard error of the first distribution is 0.49, while the second is 0.51. Okay? And then, so you are talking about the standard error. The standard error is just the standard deviation over the square root of n, no? That's the formula of the standard error. So it's the standard deviation divided by the square root of n. And which distribution may be considered symmetric? Okay, so this is or which distribution may be considered skewed, no? So this is the simplified guideline. If skewness is greater than the product of 2 and the standard error of that distribution, then we can conclude that the distribution is skewed. Okay, skewed to the left if it is negative, skewed to the right if it is positive, no? And then the skewness is less than or equal to 2 times the standard error, then you can conclude that your data is normal or symmetrical. Okay, so basically, if you have noticed, no, although I will emphasize it later, no, where can you get the standard error? No, if you cannot get the standard error, then you have to divide the standard deviation by whatever is the number of observations that you have collected. Okay, and then you have the measures of cortuses. Cortuses actually is the degree of peakedness or flatness of the distribution. So it is the it measures the extent to which observations cluster around a central point. And then when you talk about mesocortic, there are 3 types of cortuses. You have mesocortuses, you have platycortuses, and leptocortuses. So no problem with mesocortic distribution, because mesocortic distribution is just the same as normal distribution, while platycortic distribution cluster less than a normal distribution, and usually the top is flat, no, flatter peak around the mean, and thin tails observations cluster less. It means that it's flat, no, that the top is flat. It means that this is a distribution wherein more or less the frequencies for all classifications are just the same. More or less, it's somewhat like a uniform distribution. Leptocortic, no, so cluster more than a normal distribution. Higher peak, it means that higher peak, yes, not normal, no, but usually the tails are short. Okay, so how would you determine based on the graph whether you have a mesocortic, platycortic, or leptocortic? So you have here the guideline. So if the absolute value of the cortuses is less than equal to the same, no, for skewness, no, because I mean for symmetric distribution, because symmetric distribution is just normal or mesocortic. However, if it is greater than, it is either platycortic, no, if cortuses is negative, and then leptocortic if cortuses is positive. So this is the graph looks like, no, how the graphs look like, no, for the leptocortic. You notice that it's a very high peak compared to mesocortic or platycortic distribution. So more or less, the top of the platycortic here is flat. So it means that more or less you have many of the classifications that you have are with the same frequencies. Of course, you are familiar with mesocortic distribution. For leptocortic, a good example of this is if you, for example, talk about the IQ scores of students at University of the Philippines, no? So most of the values are high, no? We consider, for example, students at University of the Philippines, no, they have, all of them have average, I mean above average IQ, no, so above average. And but all those you consider them as intelligent people or bright people, no, but there are those which you consider as super bright, no, but there are only few of them. Even if the students have above average IQ, still there are those which are non-performers. Now, then there are also a few of them. Now, that is an example of a leptocortex. So, if most values are high, no, so you would consider that not that it's skewed to the left, no, but because you know that it is skewed to the left, of course there are small values, no. You have below average, average, but most of the values are above average. And then although in SPSS now you can just check on the cortuses, no. You can just request cortuses. Okay, so we go to inferential statistics. No? So usually in inferential statistics, no, we will be testing hypotheses. No? So you have here the null hypothesis. This is the statement of equality. No? It means that this is a statistical hypothesis which asserts that there is no difference, no equality. There is no difference, there is no relationship, or there is no impact or effect due to the influence of the independent variable. While the alternative hypothesis, that is the operational statement of the experiment's research hypothesis, no? So this is the hypothesis which asserts that there is a difference, that there is a relationship, or there is an effect due to the influence of the independent variable. Usually, although I will demo to you in a while, I will teach you how to of course, you know, when you do research, of course, you know how to formulate the hypothesis. You state it in such a way that there is no relationship or no difference or no effect. And then the alternative should be the opposite of the null hypothesis. Although in current researches, usually they do not use the null hypothesis. No, they simply specify it as research hypothesis. No, so the research hypothesis is based on the literature review, no, that they did, and what have they found out, no. So for example, you have to review articles related to your study on a particular variable, and if most of your studies that you have reviewed specify that there is a relationship, it means that your hypothesis should be there is a relationship. In this case, you will call it as research hypothesis. Is there any question, guys? Ma'am Clarita, any question? Sorry. Ma'am, yeah, thank you, Sir Jonas. No, 0, you're correct. No. Okay. Well, am I too fast, guys? Nor?
Sir?
This session is recorded and they will be provided with the recording.
Yes, sir.
Okay. Guys, please tell me if I am too fast, no? Because these are just concepts that I am discussing. And then perhaps I will elaborate when we perform already statistical analysis using IBM SPSS. Please tell me if I'm too fast, such that I can also mellow down, especially if you're not able to catch up with my discussion. So far, walang question. And then you have a one-tailed test and two-tailed test. So actually, the one-tailed test, that is, if your hypothesis is alternative, no? So meaning one-tailed, meaning the direction is either. So that the one-tailed here, it will tell you whether your alternative hypothesis is directional, no? So directional, it means that perhaps it's greater than or less than, no? While when you say two-tailed test, it means that your hypothesis is non-directional. For example, when you say that there is a difference, you do not specify. Like for example, okay, your null hypothesis is there is no significant difference between the average IQ of the students coming from provincial high schools and city high schools. So there is no difference. That is your null hypothesis. Okay, your alternative hypothesis is there is a significant difference between the average IQ scores of the students coming from provincial high schools and city high schools. So there is a significant difference. You do not specify which is greater or which is lesser, then that is non-directional. So non-directional is two-tailed. However, if you specify that the average IQ scores of the students coming from provincial high schools, the average is greater than or less than the average IQ scores of the students coming from city high schools, then in this case, your alternative hypothesis is one-tailed. So actually, in the output of IBM SPSS, it is already specified there if it is one-tailed or two-tailed, no? Because basically, no, we do not, no, when we try to write the manuscript of our research, no, we only specify the null hypothesis. No, we do not include the alternative hypothesis. However, in a different case, no, in a different scenario, if your hypothesis, you have research hypothesis, that would be a different case, no. But usually we test hypothesis based on the null hypothesis. So there are two types of error in hypothesis testing. You have the type 1 error, that is when you reject the null hypothesis when it is true. Perhaps because of the sampling, no? Perhaps the sample is not representative. So type 1 error may occur. So you reject the null hypothesis when in fact it is true, when it is not false, no? And then type 2 error, that is when you accept the null when in fact it is false. So accept meaning fail to reject, no? Because there are some statistics books that they don't want to use accept the null hypothesis, because accepting the null hypothesis, it doesn't necessarily mean that it is true. Okay, so that's why they want to say that to conclude that fail to reject H of 0, but it's okay, no? Whether you conclude that accept HO or reject HO, what is important is what is the implication of your results. So this is a table that presented the 4 scenarios, no? Now, for example, you decide to reject the null hypothesis when in fact it is true, type 1. No? So there is an error there. But if you reject HO and then HO is false, yeah, it should be rejected because it is false. So therefore, correct decision. And then you accept, you do not reject, or instead of failing to reject, no, other authors would prefer to use do not reject. So do not reject HO when it is when you accept or when you do not reject HO when it is true, of course it is a correct decision because it should not be rejected because the hypothesis is true. However, if you accept, if you do not reject when in fact it should be, then there is an error there. That is type 2 error. Okay, just to give you an example, actually we have written a book for senior high school, no? So actually we have published a book. We call it Seeing the World Through Probability and Statistics. And actually we are 4 authors of this book, and I did chapters 4 and 5, which is about estimation and hypothesis testing. So let me just share with you parts of the book which talk about hypothesis testing. So I did chapters 4 and 5. Okay, perhaps just to give you some examples of the null and the alternative hypothesis. So you have here, for example, the following are examples of statistical hypothesis. And you say the average grade of all students in the statistics class is 85. So is equal. So that is null, no? So the alternative, the average grade of all students in a statistics is not 85. So this is alternative, no? Specifically non-directional alternative hypothesis. And then you have the percentage of Cebu City College students who prefer the taste of Coca-Cola is 2/3. So percentage is proportion, so equals 2/3, and then the alternative is less than 2/3. So this is alternative, directional, no, to the left. And then the proportion of voters who favor the mayor is 40%. So T is equal to 0.40, and the proportion of voters who favor the mayor is greater than 40%, no? And then there is no significance. So this is what I have given as an example. The average IQ of students coming from provincial and city high school, there is a difference. Okay. For example, you have state whether each hypothesis is a null, a directional, or non-directional. Number 1, a new advertisement will improve the sales of the product. So will improve, that is directional. There is a significant difference in the preferences of movies between Gen Y and Gen X. That would be, there is a significant difference, no? So meaning this is non-directional. Number 3, young males play Dota often than their female counterpart. So this is directional, more often. And then number 4, the average time for social laptop batteries to be fully charged is 45 minutes. So is equal, therefore this is null. The proportion of sure users is higher than 50%. So is equal, higher than, sorry, it's higher than, it's directional. Okay, we talk about type 1 and type 2 error, no? So type 1, this is the error committed when the null hypothesis is rejected, when in fact it is true. It is symbolized by alpha. So you have here an example. Jack is scheduled to date Rose tomorrow evening. Pag-asa has announced over the radio that a typhoon is going to hit tomorrow with 5% chance of occurring. Jack was advised by his parents to move the scheduled date with Rose. So note that Jack is confronted with weather. So usually, null hypothesis is status quo. So it will not rain tomorrow. And then the alternative, it will rain tomorrow. So this is your null. This is the null hypothesis of Jack. The alternative, no? Jack decided to follow the advice of his parents. So he cancels the date. So, because the advice is to move the schedule. So it means that rejected, no? Jack rejected the null hypothesis that it will not rain tomorrow, but the next day, so it did not rain. So therefore, Jack here committed a type 1 error because he canceled the date when in fact it did not rain. So rejecting the null when the null is true, that is a type 1 error. Okay, type 2 error, that is when the null hypothesis is not rejected, when in fact it is false. So you have an example here. A drug company claims that their drugs are effective in preventing a common cold or colds, no? To check the claim of the company, Anna selects a random sample of individuals and asks them if the drug was effective and recorded the proportion of individuals who answered yes. She decides that she will reject the null hypothesis only if the results were significant at the 0.05. No, so she conducts a test of statistical significance using tests concerning proportions, no? Because what is the proportion for yes, what is the proportion for no? So test concerning proportions and finds that it is significant at the 0.003 level. The result, no, based on her data, it's 0.03. Now, she did not reject the null hypothesis because she sets no, the alpha level is 0.01 and then the p-value that she got, no, based on her data was 0.03. Now, this is greater than 0.01. Of course, if this is if the calculated is greater than the standard, then you have to accept the null hypothesis. You did not reject the null hypothesis. Okay? In hypothesis testing, literature indicated that the p-value of 0.05 or lower justifies the rejection of the null hypothesis. No, so 0.3 man siya. So, dapat she should reject the null hypothesis because basically, no, in hypothesis testing, usually we use a standard of 0.05 and 0.03 is less than 0.05. No, although she set it's 0.01, but actually it's okay if the p-value was set up to 0.05 because literature, no, I believe that most of you are familiar that the usual thing that we use is 0.05, no? So in this case, Anna committed a type 2 error. So she did not reject the null hypothesis, and in fact it should be rejected. Let me go back. Okay. Now we proceed to categorical variables. Guys, I will be skipping some of this because we have this. Perhaps I will just ask somebody, no, to volunteer, no, for the particular exercise. Describing categorical data or qualitative data by the use of frequency table. So a list of values that a variable takes in a sample, it is usually a list ordered by quantity showing the number of times its value appears. So to execute descriptive statistics frequencies, and then move the variables that you would like to analyze in the variable list box, and then you may click charts, no? And then choose bar in the chart type. So you have only three options there, no? Bar, pie, and histogram. But the histogram is basically used when the data are quantitative. And then you can make use of the percentages instead of frequencies, no? For the chart values. So it's up to you, basically. And then the pie chart, actually for qualitative data or categorical data, you can also use, instead of the bar graph, the pie chart. So you have, basically the same, but instead for the chart, instead of using or choosing bar graph, you use the pie chart. I mean, you choose pie chart. And then usually for the pie chart, we should use the percentages, no? Because the pie chart actually presents the percentage distribution. Okay. So this is activity 2.0 using the GSS 2002 dataset. So you have to do frequencies, no, for race, sex, post-life, health, not aid, news 30. Then use bar chart and then percentages. And then you present nor.
Sir?
And we have the first what? This is
First.
I am giving an activity. So
Same na lang, sir. First two.
But should we encourage the others, no? We give chance to those who were not chosen yesterday.
Yes, sir, please.
Okay. So guys, using the GSS 2002, I know that you can do this.
GSS 2002.
Thank you, Ma'am Karina. Please be a little bit slower for the activities later. Thank you, Ma'am Karina. Oh, activity 2, Ma'am Sir Tristan. Let me check. Automatic Sorry. Dapat wag download. Diba ako nag-download? Kaya pa nag-download ako ng... Bakit pinapa-download nila? Ayan. Tapos, si Sir Tristan. Yes, Sir Tristan, can you share your output? 1, 2, 3, 4, 5, 6.
Yes, sir.
activity.
So Christian, can you scroll down? Okay.
Scroll down, sir.
Okay. Can you explain, Sir Tristan? What did you do?
Okay. Sir, firstly, I open the file, then click Analyze, descriptive statistics.
Sir Christian, we cannot see your screen. Yung output pa rin yung naka-share. Okay, yan. Okay. Okay na po.
Tapos, nag-feedback po yun. Okay. First, after opening the file, I click Analyze, then descriptive statistics, frequency, no, then the box here, the frequency box. Okay. And then I have selected, let's put them back. Sex, race, not ID, post life, health, news 30, and then put them in the variables box here. Then select chart, select bar chart, percentages, continue, then okay.
You go to the output screen.
And here's the output. We have the bar graphs here, the percentage for the respondent sex, race, the federal spending on foreign aid, belief in life after death, condition of health,
News 30.
what's this? Our used news site and web in the past 30 days,
Okay.
and that's also.
Thank you. Thank you, Sir. Sir... Sino ba yan? Sir Tristan ba yan?
Yes po.
Okay. And then, and then the next one was actually, sino ba to? Tristan. Si Romel ba? Romel yata. Yeah. Romel Pasqua. I think Romel also got it right, no? So Nor, si Romel Pasqua, and then Tristan Pareñas.
Congrats. Noted, sir.
Thank you. Thank you. Thank you, Sir Romel and Sir Tristan, and also Sir Jo Marino. Sir, you are good with the pacing for it. Okay. Okay. Thank you, Ma'am Karina. Sir Jonas also has shared his results. Okay, let me proceed. So we go to categorical versus categorical. So cross-tabulation using more specifically on the chi-square test of independence or the chi-square test of relationship. So the most commonly used test of relationship is the chi-square test, no? So you call it as the chi-square test of relationship or the chi-square test of independence, no? That is if your data are both categorical or qualitative. So cross-tabulation, when we talk about cross-tabulation, meaning you have rows and columns, no? And then your data are frequencies. So the objective of this presentation is to determine whether there is a relationship between two categorical variables. So comparing groups for categorical data, so cross-tabulation, so a basic technique used to examine relationship among categorical variables. So this is the output variable, no? So usually you have the row percentages na indicate the distribution of gender for its response in belief in life after death, no? Whether they believe or not, no? For example, you would like to determine if there is a relationship between the respondent's sex and their belief in life after death. Okay, so you have here those who believe. For males, 425. For the females, you have 550, no? And then for those who do not believe, 138 for males and 98 for females. Okay, and then you have the percentages, no? As well as the total. Both for total for the column as well as for the total for the rows, no? And then you have the overall total here is 1,211. So the column percentages indicate the distribution of response, no? Yes or no for each gender. The column percentages. Column indicate the distribution of response, no? Sa column, yeah, for male and fail, no? How many from the males who said yes, as well as for the females, and how many said no. So the chi-square test of independence or relationship is a statistical tool that summarizes the discrepancy between what is observed and what we expect under the null hypothesis. What is the meaning of this, no? Meaning, when you say under the null hypothesis, because your null hypothesis, it should be stated in such a way that there will be no relationship. So if there is no relationship, it means that the frequencies for all cells should be equal. So under the null hypothesis. When we collect data, we seldom collect results wherein we have the same frequencies. There is always a discrepancy, no? So would like to check whether that discrepancy is enough for us to reject the null hypothesis, to tell us that there is a relationship. The null hypothesis is assumed that there is no effect in the population. Here, the men and the women show no differences in belief in life in afterlife or gender and belief in afterlife are independent. That is why in stating the hypothesis for the chi-square test of independence or test of relationship, if you want to use test of independence, you can say that one variable is independent of the other. And then the alternative is one variable is dependent on the other. So you're using here independent and independent, no? However, it's also equally it's the same when you say your null hypothesis is when you say one variable is independent of another, it means that you can also say it as there is no relationship between the two variables. And then the alternative, one variable is dependent on the other. You can also state it as there is a significant relationship between the two variables. So, belief in life after death is categorical and male-female is also categorical. So, null hypothesis, pwede, no? Variable 1 and variable 2 are independent. Variable 1 and variable 2 are not independent. Or variable 1 is dependent on variable 2. So, we have to use descriptive statistics and then cross tabs, no? And then, so we have to click on statistics and then choose chi-square and then click the cells push button and then you have to check expected, no, in the counts area and then continue and then okay, check. So what is this data all about? Still the same. So for example, no, if we open our GSS 2002 data, how do you do chi-square in IBM SPSS? GSS, this is day 1, so day 2, so day 2. GSS 2002 data. So everyone, you open your GSS 2002. I believe everyone has opened it already because we have an exercise a while ago. Okay, so you have the GSS 2002 data. So we'll have the gender is the column and the row is the belief in life after death. Okay, and then expected in the country. Okay, so you have analyze, descriptive. Under descriptive, you have their cross tabs. Cross tabs. and then right click. Your row is belief in life after death. What is that variable? Life? No, it's life exciting. Let me check. Variable view. Belief in life after death. Belief in life after death. This one. Post life. Post life. So, analyze, descriptive, prostobs. Your row is post life. And then your column is the sex or the gender sex. And then statistics, you choose chi-square. And then continue. And then we are asked to click cells. And then what was the instruction? Check unexpected on the counts area. Expected. And then continue. And then okay. Okay, so you have the result here. No, so actually it is Pearson chi-square, no? Actually chi-square is Pearson chi-square. So you have the p-value there is 0.001, no, which is significant, no? So it means that since the p-value is less than 0.05, it means that there is a significant relationship between gender or between sex and respondents' belief in life after death. Oh, by the way, I just like you to you have here the count, no? So the count, this is the result of your you call this, of the actual survey, no? You ask your respondents whether they believe in life after death or not. So these are the actual data that you collect, no? The expected is this should be the supposedly count if we consider the null hypothesis, no? Meaning that no relationship. If these are the counts, now we expect that more or less if this is close to these values here, it means that there is no relationship, no? But in testing the significance, no, or whether there is a discrepancy between the expected and the actual count. So you notice that what is the difference here? More or less the difference here is 28, no? The difference here is also 28. Difference here is 28. So it means that the difference na 28 matters. So that for us to conclude that there is really a relationship between respondent sex and their belief in life after death. And then usually because that's it, no? You just say that there is a significant difference. I mean, there is a significant relationship. But what is the relationship? What does the data tell us? Usually, what I do, to give some insights on the results, no, I try to check the display clustered bar charts, no, so that I can see what is the pattern of the relationship? Okay. So now call this can guide you on how to interpret the results now that there is a relationship. So what is the trend? Usually the females, more females, no, the trend, more females believe in life after death compared to the male respondents. Yeah, consistently also more males do not believe in life after death. You see that, guys? You understand? Because the chi-square will just tell you that there is a relationship. So what is the trend of the data? What does the data tell you, no? Or what does it tell us? So based on the graph here, you would see that the discrepancy between the two, no? So the females, you notice that the proportion of them who believe life after death is greater, no, compared to the men. And also the men, there are more. The proportion of males who do not believe in life after death is greater compared to the males. The two are consistent basically. And in some cases, you can also use, in your analysis, crosstabs, you can check on Kramer's V, to determine the degree of relationship. Kramer's V. Uh, 0.11. It's significant actually. By the way. So the chi-square tells us that there is a relationship. But for whether it is significant or not, you have to consider Kramer's V. No, so it's less than 0.001. It means that there is a relationship, and the relationship is significant. Now that there are more females who believe in life after death, compared to the male respondents. Any question or clarifications? Okay. So I believe that we have already interpreted the results, no? So you have the expected count. No? So that is actually in manually, how do you compute for the expected count? That is the column total times row total divided by overall total. So it means that 563 times 975 divided by 1,211, that is 453.3. Same here, that is 648 times 975 divided by 1,211. You get 521.7. Here, that would be 563 times 236 divided by 1,211. You get 109.7. This one, 648 times 238 divided by 1,211. So the residual is the difference, the one that I'm telling you, the difference between the actual or the observed and the expected, no? So we expect here, like for example, 28. Difference of 28. Yeah. So we interpreted the probability, which is the p-value, the Pearson chi-square. That is, it will tell us the relationship. There is a relationship, and to test whether the relationship is significant, we use Kramer's V for nominal versus nominal. Okay, there are actually other measures of association or relationship. No, it depends upon the type of data that you have, no? So you have Lambda and Goodman and Kroskal-Stow. You have, I discussed to you. So these are the chi-square based, no? So I discussed to you the Kramer's V. And there are also other types of chi-square, the phi coefficient and the contingency coefficient, especially if you have a 2x2 table, no, and then you also have ordinal. Usually for ordinal, we use a Spearman, no, but there are also other types, no. It depends upon the type of data that you have, and then Pearson's R, no, this is the common one, but actually there is a course that you call non-parametric statistical tools, no? So it will discuss to you the different types of statistics, no, for determining relationships. Depends upon whether your data are nominal ordinal, nominal interval, nominal ratio, ordinal, interval. So it's actually different course, no, or a different session, no. Perhaps StrandAsia can create a program that will focus only on this, no, the measures of association, no, that is categorical, no. Actually in our course in the UP School of Statistics, we call it categorical data analysis, and you will encounter these different statistics that determines association. But the most commonly used measures of association for categorical chi-square test of relationship or the chi-square test of independence, and then you have Pearson R, or the Pearson product moment correlation coefficient, which we are going to discuss in a while. Also have ETA, McNamara statistics. I still have my notes on this, no? When I studied my master's in the LSU, we call the course non-parametric statistics, and most of the examples in the book that we use, actually it's non-parametric statistics by Castellan. Most of the statistics, I mean most of the applications that were discussed in the book are related to the medical field, as well as in psychology, psychological statistics involving patients. Usually talk about patients. Usually the number of participants that are involved in the study are not that too many, so that's why it will call for the use of non-parametric statistics. And also you have the Cochran and Mantel-Haenszel statistics, especially if you're going to use odds ratio in logistic regression. Okay, you have an exercise here on chi-square. So run cross tabs for race against health, not aid, news 30. Run the chi-square test of independence And then you repeat the analysis after substituting sex in place of race, no? So actually you can do it simultaneously, no? You can have, for example, if your race is the column, then your rows would be health, not aid, news 30 at the same time, no? You can do it at the same time. And then, so you run the chi-square, no? And then, perhaps, no, based on your result, okay, based on your result, no, you make a table, perhaps, for race and sex. Then, okay, so what are you going to do based on what you have run, what you have performed, your analysis? So you must have perhaps one for race and one for sex, no? Or perhaps it depends upon, I think we need two for race and two for sex, no? So you must have a table, no? So here the types of chi-square and then the p-value. So the p-value and then so types of chi-square. So you have, for example, for health, no? And then not aid and then use 30. And then you specify what are the p-values and then decision. Decision is whether you reject or you accept HO. And then conclusion, whether you have to specify na conclusion, there is a relationship or there is no relationship. And then after that, you run, you replace race by sex, and then you run again the data versus the 3. And then the same. So you present your table, and then of course it should be supported with your output, no? I will also ask the output. Nor?
Sir, yes po.
Can we have 4 this time?
4. Sige po.
Dalawa for race and dalawa for sex.
Alright.
Okay. So guys, I'd like you to do this this exercise. And then I again the first two, but of course let us consider we have to give chance to the others who have not presented yet, no?
Yes, please.
And then yeah, I think the last topic on scale variables. So perhaps Nor mag-breaks muna tayo and perhaps siguro baka yung iba hindi magbe-break, magpo-perform sila muna bago mag-break. In how many minutes, Nor?
15 minutes, sir.
So 15. So we'll be back at what time is it now? In my computer it's 10:16. So 10:31.
10:31.
Okay. And then when we come back, I would like you to present. I will choose from the chat box, no? Especially I would like to have the table presented in this form. So I will choose 2 for race and then 2 also for sex. Hello? Guys, can you hear me?
Yes, sir.
There's a question from Ma'am Hanilu. For a while, my computer is loading. There's a question here by Ma'am Hanilu. Sir, what do you usually do if more than 20% of the cells have expected count less than 5? If the chi-square Actually, I have tried experimenting on this. So what would be the impact if I will remove a certain frequency, I reduce, like for example, if I have 5, and then I make it 4, I make it to 3, I make it to 2, I make it to 1, I make it to 0. And then I computed the chi-square, and I found out in my experiment that still, if it is significant, it will be really significant, and if it is not significant, it is not significant. Actually, I'm writing a paper on this, a research on this, experimenting on reducing the frequencies to less than 5, and until it becomes 0, and then computed the chi-square in the same situation, So basically, I have found out that when the result is significant, then it will be significant. When the result is not significant, then it will be insignificant, even if you are going to reduce to have a cell less than 5, okay. That is what I have observed, but Ma'am Hanilu and then the rest, and then we are the one collecting the data, we are the one collecting the data, especially we are doing a research, and then we are going to use the chi-square. So question here
Recording
is
in
that
progress.
since you are collecting the data, even if you are done collecting data, perhaps you can increase the data such that you will not encounter a cell which is less than 5. Or there are actually other statistics, there are also other statistics equivalent things that I have presented, the association measures the different statistics, so we know that the use of statistics actually usually will employ small sample size, but we can still we can find a solution to that by trying to look for other samples, just to increase the frequencies for a particular cells. Ma'am Hanilu, I hope I have addressed the question, So since we are the one collecting the data, so probably you can increase such that you will remove, or you can have a cell which is which is at least 5. Except for those, if we have an exercise for our students, there is a cell which is less than 5. That is something that we can no longer control. Let me check activity. We have Sir Floresco Franco. Sir Floresco, can you share the result? Yes, sir. Sir Floresco, can you share screen po? It means that there is a relationship between the condition of health and okay. Yeah, more white or with excellent. No? Yeah, very good because you at least showed us what is the trend of the relationship. And then the second, okay, okay, okay. Thank you. Thank you, Sir. Who is this? Sir Franco Flores. So, Sir Flor, thank you. Nor, I'm happy, because our participants are really very good, in
Yes, sir.
action. They know already how to explain the results, no? And very,
Yes.
yeah. Thank you, Sir Flor. And then, so
The
that
other one, sir.
the other one is, so Sir Flor. After Sir Flor is Sir Jonas. Nakahapon, nag-present na ba si Sir Jonas kahapon? Sir Jonas? Sir Jonas? Si Sir Jonas, you have Sir Romel, tapos na rin po Sir Tristan. Si Sir John Marie, Sir John Marie,
Sir Jomari, sir, yesterday.
tapos na si
Si
Sir.
Sir Jonas po ang wala po yesterday. Yesterday si Sir Jomari, si Triel, si Don Dexter, and si Ma'am Honey Lou. So
Okay.
Sir Jonas, wala po.
Sir Jonas, can you present Sir Jonas Paul de la Cruz? Sir Jonas. Sir Jonas. Yeah, sir. Sorry, can you present, sir? Sex. Do you have the result for sex or are you done with the exercise, Sir Jonas? Yeah. I think you have done both for sex and race, no? Yeah, so can you present the result for sex because Sir Chris, what was that? Sir Floresto had presented the results for race. So can I ask you, sir, to present the results for sex, the relationship between sex and those variables mentioned? Thank you po, thank you. Uh-huh. And then it's what? It's greater than, there is no there is no relationship, no? Or it means that men and women equally are prone to diseases or illnesses. Yes, sir. Okay. Dependent. Yes. Use. Is less than 0.05 po. Is less than, meaning there is a relationship between respondent sex and then whether they use the web, no, to to watch news, for example, in the past 30 days. And then what is the trend in the data there? You compare the male and the female. More females on pero pag more, that less than at saka less than 5, ano? Correct. Correct. Yeah. Thank you po. Thank you, Sir Jonas, no? Honor, Sir Jonas and Sir Floresto. I do not know if there is another.
Noted, sir.
Yeah, Jo Marie, Tristan already done. Okay. Thank you, guys. No, so yeah, very good, everyone. Because please, you know how to run IBM SPSS, no, for determining relationship for qualitative variables, no, particularly the use of the chi-square. You know also how to interpret, no, then do the explanation. Okay. So we proceed to the next topic, which is about scale variables. When you talk about scale variables, it means that we're talking already of quantitative or numerical variables. While computer again is loading. Okay. So scale variables, descriptive statistics, exploratory analysis. Scale variables, so the objective is to determine the appropriate exploratory analysis for scale variables, for numerical variables, to be able to interpret graphical outputs. So scale versus scale, meaning quantity versus quantity. So what is the purpose of doing descriptive statistics? No, it will provide us the summary of the data or of the observations, which may either be quantitative, or perhaps visual, exploratory analysis, approach to analyzing data to summarize their main characteristics, no, usually in the form of visual methods. So we have here an activity. So for exploratory analysis and descriptive analysis, no, just to determine the skewness and kurtosis of the data. No? So you have the variables rs1, sieves, childs, and age. No, I think this is still GSS 2002. No, so click analyze descriptive and then transfer the variables rs1, sieves, childs, and age into the variables box. And then click options and then check skewness and kurtosis. And then click continue and then okay. So the histogram displays the distribution, the range and concentration of dataset consisting of either interval or ratio variables or scale. So as we have discussed earlier or yesterday, that if the data are qualitative, the most appropriate graph is either the bar graph or the pie chart. However, if the data are numerical or scaled, then we have to use the histogram. Adjacent data values are grouped together so that each bar represents the same range of data values. I think there was a question yesterday about constructing the histogram, no, on automatic. If you're going to use, for example, Excel, we can construct frequency distribution, no, by because it's automatic. You have the bin range. We only have to specify the bin range, and then Excel will automatically output us, will give us the frequency distribution table. For IBM SPSS, we have to transform the data to be able to produce the histogram. So this is an example of the histogram. So you can see here that more values are concentrated more or less at the middle, no? So you're given there the mean and the standard deviation. More or less, since more values are concentrated, no, perhaps we can tell whether we can say that the distribution is normal, no? But of course, it will depend on the value of the standard error, no, compared it with the skewness. So the standard error is just the standard deviation divided by, so 15 divided by the square root of 1763. And then we have requested for the value of the skewness, and then perhaps we will compare, no, and we had the guideline earlier, no, if it is greater than 2 times the 2 times the standard error, that would be skewed. But if it is greater, less than or equal to, that is symmetric. And then we can also do the stem and leaf display, no, for our data. Now we're in, like, for example, if you have 55, 58, no, if you have a 2-digit number, so the stem there is 5 and then 8 is the leaf, no, that is the number of leaves. Basically, what is the purpose of the stem and leaf display? It can also tell us more or less the shape of the distribution, whether it is skewed or whether it is normal or symmetrical. So this is an example of a stem and leaf display. You would see here that more or less the more values are concentrated at the center, no? If you are going to rotate it counterclockwise, more or less you will see that it is somewhat normally distributed. And then we talk about the box plot. No, the box plot is another graphical representation of scale data, wherein you have a box or a rectangle plotted at the Cartesian plane, And then in the box plot, now you have there the edges, no? So usually the left side, no, that is the position of the 25th percentile, the edge to the right, no, and I mean to the left, and then to the right, that is the 75th percentile. And then usually the 50th percentile is at the center, at the middle, no, in between the edges, no. It is at the center or the middle in the box. And then if there is in the graph, no, in the box plot that is represented by a circle or a dot or an asterisk, it means that that observation is an outlier. Of course, you have to consider the minimum and the maximum. What is the highest value and the smallest value? And then if it is not within that range, no, the minimum, the maximum, especially if it is outside and it is represented by if there is a dot or an asterisk or a circle, it means that observation is an outlier. So outlier is represented by a circle, is a data far from the hinges by 1.5 box lengths. So the 1.5 here is actually a constant, no, because the formula to determine whether it is an outlier is actually Q1 minus 1.5 times the interquartile range, no, for to the left and to the right, that will be 1.5 Q3 plus 1.5 times IQR. Okay, just to give you because at first, no, when I started teaching statistics, I am not familiar with these outliers, no. But as I try to explore more on statistics, now I am able to identify how to determine whether an observation is an outlier or not. Okay. Boy, sorry, it's not the one. I think this is the one quantiles. So okay, just to give you some insights, no. Of course, if you talk about the different measures of positions, or particularly the quantiles, no. If you talk about the quantiles actually divide the distribution into an equal number of parts, no. So therefore, the median is actually one of the quantiles because the median divides the distribution into two equal parts, no. Once you have identified the median, you will know those scores which are the lower below or the lower halves, and then as well as the upper halves. when you talk about quartiles, so quantiles, no, so into an equal number of quartiles, from the word quarter, no, it divides the distribution into 4 equal parts. You have Q1, Q2, Q3, and Q4. Q1 is the first quartile, Q2 is the second quartile, Q3 is the third quartile, and Q4 is the fourth quartile, no? But there is no such thing as Q4. No, it's usually associated with whatever is the highest or the largest value in the data set. Okay. This is just an estimation on how to determine the quartiles, no? Although this is just an estimate. In IBM SPSS, you have there an option, especially under descriptive frequencies. You have an option there, quartiles, no? So quartiles, it means if you check that, it will give you the values of Q1, Q2, and Q3. So what is Q1? That is the 25th percentile. Q2 is just the same as the median, or that is the 50th percentile, and Q3 is the 75th percentile. So for example, you have your data set here. So of course, you have to arrange it first from lowest to highest. And then perhaps the first thing that you have to do is you locate the median. No? So the median, so since there are 8 observations, so the middle is here. So since we have an even number of data, our median is the average of the 2 middle values, no? Which is 64.5. And this means that 50% of the cases, the interpretation of the measures of position is always below. So this means that 50% of the cases are below 64.5. Why 50%? Because Q2 is the 50th percentile. Okay, to be able to identify the first quartile, so you cut the the data set into 2, and then you consider the first, and the middle of that would be the first quartile. And then the upper halves, the middle of that would be the third quartile. So your Q1 would be the middle between 12 and 24, that is 18. What does this mean? It means that 25%, because Q1 is actually equal to P25. So this means that 25% of the cases are below 18. And then for Q3, we consider the second half. The middle of that is Q3. No, so you have 80 plus 92 divided by 86. This means that 75% of the cases are below 86. Why 75? Because Q3 is equal to P75. You have another example. You have this time you have 7 observation. Add. Again, it's always a must that you have to arrange the data from lowest to highest. And then you always compute first for the median. So the median here is 207. And then you remove the median, consider the lower halves. The middle of that is 123. And the middle of this is 284. So you have Q1, Q2, and Q3. Earlier, I discussed with you quartile deviation, or Q. So this is one of the measures of dispersion that is seldom used. And the quartile deviation is IQR divided by 2. What is IQR? That is the interquartile range. And the interquartile range is the difference between the third quartile and the first quartile. Okay, so you have, therefore, our quartile deviation here is IQR divided by 2, and that is equal to 80.5. How do you interpret the quartile deviation? That is the same interpretation for the measures of spread or dispersion. The smaller the value of Q, the lesser the spread. The higher the value is, the more spread the data are. Okay, that is about, remember, Q1, Q2, and Q3, and then IQR. IQR is Q3 minus Q1. And then you talk about decile. The decile, di ba, quantiles into an equal number of parts. Quartiles into 4 equal parts, and then decile into 10 equal parts. And then you also have percentile and centile into 100 equal parts. So actually, I also demonstrated to you last time or yesterday, if you want to know, for example, the 10th percentile, the 30th percentile, the 40th percentile, all you have to do is to check the box, no, under percentile, and you have to write specific percentiles that you would like to compute. So I'd like you to take note that the median is just equal to the second quartile, because quartile into 4 equal parts and half of 4 is 2. And decile into 10 equal parts and half of 10 is 5. So the middle is 5. And then percentile and centile into 100 equal parts, the middle is 50. And then Q1, the 25th percentile, that is one-fourth is 2.5, tama ba? Yeah, that is 25, no? 25, or 1/4 of 10 is 2.5. And 1/4 of 100 is 25. 3/4 of 10 is 7.5, and 3/4 of 100 is 75. Okay, now I define here, because I would like you to know how to determine whether a case or a point is an outlier or not. So a point or a case or an observation is said to be an outlier if it is less than Q1 minus 1.5 IQR or greater than Q3 plus 1.5 RQR. Okay, so there are two criteria to determine whether an observation is said to be an outlier or not. So the what you call this? The left side and the right side. The left side is Q1 minus 1 point. It should be less than. Oh, by the way, what is an outlier? An outlier is an observation that is very, 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 very far from the usual values, or very, very low, or very, very high compared to the other observations. And this is how you determine whether an observation or a case is an outlier or not. Okay, so if you have, for example, sample here, data. So first, to be able to determine if there is a presence of outliers in this data set, we have to determine Q1, Q3, and IQR, no? So we are to determine whether there are outliers from the given data. So if you compute for Q2, now this is just an approximate, no, using the method that I presented a while ago, but actually you can perhaps the result in IBM SPSS might be there's a slim difference, no, because I'm just estimating it based on the how you compute it manually. So to determine the second quartile, of course, that is the median, no? So once you have identified the median, you consider the first half, and the middle of the first half actually are 56 and 61. So Q1 is 85.5. And then the middle of the second half is 110 and 112. So therefore, the third quartile is 111. So therefore, IQR is Q3 minus Q1, which is 52.5. Now, the lower bound, that is Q1 minus 1.5 IQR. What is Q1? 58.5 minus 1. This is the formula, no, as it was presented a while ago. This one. So that is substituting the values of Q1 and IQR. So we got a value which is negative 20.5, which means that if there are values in our data set which are less than negative 20.5, 20.25, we will consider that as an outlier. Obviously, in our data, since all values are positive, we don't have an outlier for the first condition. Okay? And then for the upper bound, that would be Q3 plus 1.5 IQR. We substitute the values of Q3 and IQR, we got 189.75. It means that if there is an observation which is greater than 189.75, we will consider that as an outlier. So based on our data, greater than 189, there are three. No, there are, yeah, tama. Okay, this is just the arranged. Now, this is the data, and then we arrange it. So there are actually 3 observations or cases which are greater than 189. It means that 200, 345, and 550 are outliers. It means that these values are very, very, very large compared to the other values. Okay, question. Sir, how do we treat outliers in the data set? Okay, actually, some outliers will provide us useful information. No, there are data set, or there are some companies that they would like to know the outliers, no, for them to give decisions, no. There are times that it will affect your data, then it can affect your data. You may remove outlier, no. So use your best judgment, no, in whether you will include outliers or not. Let me give you an example. Okay, this is an example about data, no. The data is about, there are 100 people who are applying for a car loan. Okay, and then we mentioned about the box plot. So the box plot actually incorporates the concepts of the 5-number summary. So what is this 5-number summary? That is the quartiles, no? Q1, Q2, and Q3. Q1, so talk about box plot, Q1, Q2, and Q3, and then the minimum and the maximum. The lowest, and then the Q1, the Q2, the Q3, and then the highest value. So if we have this data set, no, we will, if we are going to compute for the 5-number summary, of course, we can just request that in IBM SPSS. Anyway, we will compute for Q1 and Q3. So it's given here that Q1 from the data set is 23,750 and Q3 is 51,880. And IQR is Q3 minus Q1 is 28,130, no? And then using our formula, so Q1 minus 1.5 IQR, we have negative 18,445. If you notice in the data set, there is no negative income. Of course, if if my pay, for example, is negative, it's better that I will stop working, no? Because usually, if perhaps your income is negative, perhaps you have so many loans, or yeah, so you have a negative income. But obviously, no, so what's the use, no, of working when in fact we do not receive anything, no? But in this data set, the 100 car loan clients, na all the values are positive, no? And then, so therefore, no outliers for the first case, no? But for the second case, that is Q3 plus 1.5 IQR, we get 94,075. It means that if there is an income which is greater than 94,075, then that client is an outlier. And if I am the owner of the car company, I will approve the car loan of this client, no? Because it means that his or her income is very, very, very large compared to, very, very big compared to the others. So 94,075, if you notice, you have 101,600. This is an outlier. 110,300 and 149,700. So there are three outliers in the observation, and in the box plot, it is represented by a circle, no? So this one is outliers, no? There are three outliers, and actually this is an example of a box plot that is presented vertically. The usual is you present it horizontally. So this is the minimum, which is 16,400, meaning that is the lowest income. And this is the maximum. The maximum does not include outliers. So 149,700. And this is the position of Q1, whatever is the value corresponding to this one. This is Q2, and this is Q3. Okay, so that is how you read data, no? Quantitative or scale, variables, interval, or ratio. Okay. For example, guys, no? So we will rotate, okay. If it is what? If this is the box, no? For example, if the Q2 here, the middle is near siya sa Q1, it means that the distribution is skewed to the right. Skewed to the right. Okay. If you rotate this counterclockwise, no, clockwise, which is longer? This one, this is actually whisker, no? Kanimurag letter T. We call this as a whisker. If the whisker is longer to the right, skewed to the right. If it's longer to the left, skewed to the left. You rotate it clockwise. Diba? Longer to the, if longer above, skewed to the right. If longer below, skewed to the left. Okay. I think this has already been explained, no? The box plot. So, yeah. Symmetry in box plot, I have discussed this already. If it is near 75th, skewed to the left. Near 25th, skewed to the right. Okay, this is so this is when you present the box plot horizontally, you know. So you have, this is the minimum, this is the maximum, and these are outliers, no? Considered to be outliers. No, but this one is very an asterisk, very extreme already. So these are outliers. So this is Q1, this is Q3, and this is Q2. You notice that longer to the right, skewed to the right. Okay, so this is an exercise. You have using again GSS 2002. So you explore, no? Explore descriptive and then explore using RS1, WWR, TVRs to the dependent list box. And then under options, exclude cases pairwise, then continue, and then click plots, histogram for descriptive and dependence together, and then box plot, continue, and then okay. So, can you do this exercise, activity 2.2? Let me just check now what is next. Oh, what page? What? Oh, 38, 40. Still have 30 slides per, yeah. Okay, so this is an activity. No, I will ask volunteer, no, to present. Now, for the interest of time, no, perhaps I can just anyway, I've given you adequate discussion, no, discussion about. So let me just show to you, no, how to get to arrive at. Oops, oops, sorry, so no. Okay. What did I close? Kung di close, I don't know. No. Okay. So, analyze and then descriptive statistics explore. So, what are the variables? The dependent list. You have R's. Just copy it first. You have R's 1, WWR, PVRs. There are 3. You have you have R's1, you have WWR, this one, and then TVRs. And then options. Then options, exclude cases pairwise. Continue, and then plots, no? Plots, the histogram. So we will uncheck stem and leaf, and then dependence together. And then box plot. We check on where is options. Menu plots. There is no option for box plot. Okay, perhaps plots. And then I think both. This is already both the statistics and plots. Yeah, tama in the box. In the box plot. Okay. Continue and then okay. So you have here the result. So you have here like for example, no, you have the skewness and then you compare it to the standard error, but you have to multiply first by 2, no, to check whether your okay. So if you multiply this by 2, that is just 1. This is the standard error is this one is greater, no? Guys, skewness is greater than the product of 2 and this. Let me just be sure, no, of the guideline. Which part is it? Yeah, this one. No. This one. Skewed siya if greater. Kung less than equal to the product, that would be symmetric or normal. You get it, guys? So this one, if you multiply this by 2, this is the standard error. If you multiply this by 2, the result would be, what is that? Multiply it by 2. No. Na lang. If you multiply this by 2, that is 18, 1, 1 by 2. 0.118, no? 0.118. And this one is greater. But pasabot, I mean, what it means that our number of hours work per week is not normal. Our data is not normal. For hours per week, times 2. Of course, this will be also greater, really not normal, no? This one also not normal. Actually, our data is skewed, no? So which means that we have to do some transformation, no? Especially if the statistical tool that we are going to employ to use is very strict, no, when it comes to the normality of the data. So this is some of the exploratory analysis that you can do with your data, no? So basically, no, this one is not normal, no? Yeah, this one is skewed. No, this one is also skewed. Based on the histogram. Okay, and you have here the box plot, no? So there seems to be outliers, oh. There are so many outliers. So that is for exploratory analysis of your data. You understand? Do you have any questions or clarifications? Where is my Zoom? This one? This one. I will, no. I'll proceed. Let us proceed. Okay, so perhaps another activity. Now you run exploratory data analysis on age and email R. So number of hours spent on email per week. That is the email. So age and email. So this is your dependent. So do an exploratory data analysis for age and email R. The same thing that I did for an example a while ago. And I need perhaps one volunteer. Perhaps there is a question. I need volunteer, no, for kuan. Let me just check some questions here. Oh. Si Donna. I do not know Donna. Okay. Can we ask Nor? We need one prize for this activity.
Okay, sir.
So, Ma'am Donna, can you
Yes, sir. Good afternoon.
explain?
One minute, sir. So, this is the histogram for the frequency of the ages of the respondents. While this is the histogram for the email hours per week for the respondents, and this shows the plot for the age of respondents and emailers per week. So for the age of the respondents, we can see here that the minimum value or the minimum age of the respondents is about 18. And the maximum age of the respondents are about 90 or so. The median
Is it
is
right?
at 46 or something years. So, as we can see here, the skewness would be um since the median is near the minimum or the 25th percentile, it is skewed to the right. And same is true with the email of the respondents.
So basically, both are skewed to the
Right.
no? But more outliers, no, for email hours per week.
There are a lot of outliers and extreme values for the email hours.
Okay. Yeah, that's correct. Correct, Ma'am Donna, no?
Yes, sir.
Thank you, ma'am. That's correct. Thank you, Ma'am Donna. So, Nor,
Yes, sir.
so, a house and lot for Ma'am Donna. Anyway, I believe it's 11:42. Can we end the
The morning session.
so that for this afternoon we can start with categorical versus scale, the different t-tests, ANOVA, and then regression. There are a remaining 30 slides, but yeah, so perhaps for the PowerPoint presentation, I can just discuss a few of them, no, which we will share in the afternoon session. Okay, Nor?
Okay, sir. What time po yung resume natin, sir?
1 o'clock because
1 o'clock. All right. Early naman po yung yung end natin for the morning session.
Yes.
All right. So, see you po at 1 o'clock, everyone.
So I think yeah, the others are already standing, so perhaps to take their lunch also.
Yeah,
So,
okay.
see
Sige,
you.
sir.
Okay.
Happy
Bye.
lunch, everyone.
Okay.